covalence only donate 2, not octet, not whatever, how to become stable. And because there's another factor which determine they actually also can become stable even not in octet. That because you study already, there are plenty examples, not to say plenty lah, okay, there are examples where even after share electron, they're also not octet and yet they are stable. So for this one will be similar. They may not need to donate all the valence and yet they still form stable compound. Okay, so that's why group 14 a bit unique lah. Okay, they can have 2 different oxidation number. Okay, but of course you need to know transition they can have more than 1. So it can be 2, can be 3, can be 4, can be 5. Okay, so for this one only 2, and it's only shown in the formation of oxide, especially lah. Chloride got lah, but less stable lah. Okay, most of the chloride will be 4 with 4 coordination number. Okay, so let's go through this part. Of course, we start with tetrachloride first. Okay, tetrachloride. Let me all get it lah. Let me Cl4. Okay, so all elements in group 14, okay, they form simple covalent molecules of tetrachloride. I mean, it's just a molecule, consists of 5 atoms. That's all. With, of course, in a tetrahedral shape. Okay, tetrahedral, that means all group 14 able to form this type of chlorides, okay, which of course simple, just 1 unit like this. Okay, so of course to do that, the atom of group 14 elements, of course they need to undergo sp3 hybridization. Okay, I think this one also nothing new to you. You studied last semester when we are dealing with covalent bonding. Okay, make it very simple. That means when you look at carbon, isn't it? Of course, if we are looking at electron arrangement, carbon 6 electrons, so arrangement 2, 4. That one I think quite obvious. We all see that it can share 4 electrons with 4 other atoms, for example. But when we are talking about orbital, it seems like no, because that 4 valence would fill in the s orbital and the p orbital. Now s orbital already filled 2 electrons, so left 2 more. So that means it seems like in the p orbital only 2 unpaired spin. S already paired up. So that means if you look at that point of view, how you want to show that it can share with 4 other atoms. After all, only 2 unpaired spin. That means only can share with 2 others. How to share 4, isn't it? So that's when you study hybridization, right? Okay, of course, after it undergoes hybridization, sp3 hybridization, then it is going to have 4 unpaired spin. So it can, share with 4 other atoms. So in this case, we are talking about sharing with 4 chlorine atoms. So forming 4, metal chlorine bond, which is of course a covalent bond, a single bond. Okay, each of them contribute 1 electron to be shared together. So of course, if you still recall this one, isn't it? So the s orbital, the p orbital in terms of energy. So s orbital lower energy level, so it draw below. So this one is the so-called 4 valence electrons, isn't it? So the p orbital out of the 3, empty p orbitals, or should we say 2 already filled up with single spin, the other one is still empty. Okay, so when it becomes excited, undergoes sp3 hybridization. So one of the electrons from the s orbital promoted to that empty p orbital. So of course, once this reaction takes place, then actually all the 4 spin or all the 4 electrons will be equivalent in terms of energy. Okay, that means degenerated. They're all having same energy level, so that is what we call like sp3, isn't it? So of course, this sp3 having different shape from the original s orbital and the p orbital, and of course they are going to arrange themselves at four different corners of the tetrahedral, isn't it? So you're getting the structure of tetrahedral. Okay, with the bond angle between each of them would be about 104, 107. So more or less that would be the case. So that's why all the tetrachlorides of group 14 will be having a tetrahedral shape. Okay, very good revision on what you studied last time. Okay, so we start with the first one. So CCl4. Of course, if you want to follow the others pattern, yes, nothing wrong. Some of you maybe you would like to pronounce, or should we say name this tetrahedra as carbon tetrachloride. Okay lah, not to say wrong lah, okay, but of course you should know CCl4 is tetrachloromethane. Okay, so of course this one is prepared by passing dry chlorine gas into liquid carbon disulfide. Okay, and then you boil them under reflux, and of course you need iodine or iron as a catalyst. Then you find that you are getting the product CCl4. Okay, the carbon tetrachloride. Of course, in liquid form. Okay, carbon tetrachloride at room temperature is a colorless liquid. Okay, now tetrachlorides of the other three, silicon, germanium, and tin, of course, are prepared by direct combination. That means the direct reaction of the elements with the chloric gas. Okay, of course, in a heating process. So silicon heat with chlorine gas, there you get the silicon tetrachloride. Of course, again, it is a colorless liquid. Similar with germanium, okay, burning chlorine gas, you are getting germanium tetrachloride. Okay, and also tin, burning chlorine gas, you are getting tin tetrachloride. So all, of course, tetrachlorides are colorless liquid. Okay. Now, of course, for lead tetrachloride, of course, we prefer lead 4 chloride also can. Okay, this one is prepared by the action of lead 4 oxide, okay, and then react with cold concentrated hydrochloric acid. The cold means it should be below 5 degrees Celsius, so that you are getting the product of lead tetrachloride, or else the product form would decompose immediately. That means PbCl4 very unstable towards heat. You warm a little bit, it already may decompose. So you want to prepare this one, that means you need to let your PbO2, lead 4 oxide, react with HCl. And of course, the whole reaction must be kept at a low temperature, or at least, your acid must be very cold. After all, lead 4 oxide is a powder. I mean, there's no way you try to change the temperature of a powder. In lab, we cannot do that. We're only able to change the temperature of the acid, so that the whole process is happened at a very low temperature. Okay? So then your lead 4 oxide react with cold concentrated hydrochloric acid. Then you get your product, lead tetrachloride and water. Okay? Now, of course, if you let the reaction, you try to do it as the other three, you just directly hit your lead with chlorine. Of course, you don't get the PbCl4, you are going to get PbCl2. Because heating process means even the product PbCl4 is formed, immediately it will decompose. Okay, so that means, for the formation of tetrachloride, so we get 5 members in group 14. The top and the ending would be through different chemical reaction. Okay, that you cannot go for direct combination. You want to get CCl4, carbon burn in chlorine? Sorry, you don't get it. You want to get PbCl4? You want to burn your lead in chlorine? Sorry, you also won't get the product. Okay, so that means that two would go through different product. Sorry, I mean different chemical reaction. Okay, so that is tetrachloride. Okay, that how to get the tetrachloride. Okay, so now let's have a look at the tetrachloride. Some of the physical property of that chloride. Okay, first of all, the boiling point. Now, of course, all tetrachloride are volatile, colorless liquid at room conditions. When you see the word volatile, you should get it. That means low boiling point. Nah. Volatile means easily evaporate, easily change from liquid to gas. Okay, but still, it's really going to check, isn't it? Now, of course, they're covalent molecules. So, of course, the intermolecular forces of attraction among the molecules, of course, is the weak van der Waals forces. After all, volatile, easily change to gas. Okay, so that means you want to boil them, little heat is needed. Okay, that boiling point of tetrachlorides all would be low. Clear? But still, of course, how about the trend going down the group? That, of course, going down the group, size of the molecule increases. Because the group 14 element getting bigger, Cl, of course, same size, okay? But the group 14 element getting bigger. So overall size of the molecule increase. Of course, we study already. Van der Waals forces. Bigger size means stronger forces. Get that? So you find that strength of van der Waals forces increases going down the group. So if the attraction force getting stronger, of course you need more heat energy. So automatic, your boiling point increases. Okay, is that quite common to you already by now? Okay, of course, if you check in terms of value, you see, of course, very low, volatile, okay, or negative value, in fact, for melting, but for boiling, that is considered low, okay. In fact, the PbCl4, we don't really get a value for boiling point, because it will decompose, get that? In fact, slight warming already decomposed now. But normally, if you really check in terms of value, we hit it to about 105 lah, more or less okay? It will start decompose. So that means this is a liquid. You heat, then you find that actually it will change into a new product instead of turn into gas, okay? So no boiling point. Of course, if you check, when you look at this one, the weird case, carbon, isn't it? Is it? Carbon is the weird in terms of melting and also boiling, extremely high compared to the rest. And of course, so far, even though I check from books also, they don't really have a very obvious or very specific explanation for this one. Okay, so don't worry. Question will never ask you to explain. Okay, so far. No specific explanation for this one. Why? So far, books never explain why. Okay, but they did point out about this abnormal behavior. So don't ask me. I also don't know how to explain. Okay, meaning the van der Waals forces will be very strong in the molecules of CCl4 compared to the rest. Don't know why, because actually you should know it is smallest in size, isn't it? And yet how come it has all the strongest bonding? Because if the attraction is not strong, then how come it needs so much heat energy, to melt or even to boil? I don't know, okay? After all, CCl4 is only van der Waals forces. No hydrogen bond, nothing, okay? So I don't know, okay? But that would be the case. Okay, but still, of course, if this one, isn't it? I mean, PbCl4, no boiling point, of course, you should know lah. does not have normal boiling point because it decomposes when heated to a certain temperature. Then when it decomposes, how? Becomes PbCl2 and with the release of chlorine gas. So which you're not obvious how you imagine when you let your Pb react with chlorine, even though you get PbCl4, so immediately it will decompose because heating process. Okay? So that will be the reasoning. So that is boiling point. Of course, if you check in terms of generate a graph. Now this one of course not so good. Now when you are plotting a graph, make sure boiling point you must put in the unit. Okay. So here actually the best is group 14 tetrachlorides. Okay. So that means this one we assume lah based on should we say this one extra polarization? Not really, don't know. That means based on logic, you increase this one. That means we can predict maybe, let tetrachlorides boiling point be somewhere here. But of course, we have no idea because it decomposes under high heat. Okay, so that's settled for boiling point. Okay, next let's check. How about if I want to heat and let them decompose? Thermal stability means only one. You want it to decompose, produce, new products. That means just by heating, this one, not adding with any other reactant, just heat only. So thermal stability. Now, based on this part, of course, you should know already. The most unstable, definitely PbCl4 lah, isn't it? There, PbCl4, you heat, it will become this two. So this one, no need very hot. 105, enough already. And don't ask, okay, books sometimes they only put slight warming. But when it comes into value, they will put 105 degrees Celsius. 105 actually quite hot already to us. But books sometimes you read, they will just say slight warming. I don't know, the so-called slight warming is what, 20 degrees Celsius? So no idea, okay, but it just fixed to this value lah. Okay, we assume it is low. Easily decompose. So if you check thermal stability, okay, so of course you find that decreases going down the group, meanings it's getting less stable. In other words, it decomposes easier going down the group. Okay, thermal stability, that means it become it is very stable on top and yet it become less stable going down the group. Or in terms of decomposition, the one on top maybe doesn't decompose, the one below decompose easily. That's the meaning, thermal stability. Decreases going down the group. Okay, of course, if they want to ask, now that means this one is the bond length of that metal and the chlorine. Going down the group, the bond length, the distance between these two atoms increases because the element M getting bigger in size. So of course we all know if the bond is long, of course it is weak. Okay, because you need to know the bond is formed when they share electrons. If the bond is so far, if the bond is very long, meaning these two atoms far from each other, then of course the attraction between them is weak. When it is weak, of course decomposition means you want to, separate Cl from the M. Of course, M means a group 14. So if the bond is weak, easily separated, then of course it will decompose very easy. Correct? So then less energy is required to break the bond. So they are easily decomposed upon heating. Correct? And for this one, please, do not talk about polarizing power. Because polarizing power only possessed by ion. This one is not ion, no. M is an neutral atom because they share electron. They didn't donate accept, so no such thing as distorted electron cloud lah. No such thing as polarizing power. Don't use that one. Don't mention at all when you're talking about group 14, because we are talking about covalent compound, not ionic compound. Okay, so that means of course if you check now the first three very stable towards heat. That means you hit them strongly, sorry, nothing happens. Okay, now tin chloride, tin tetrachloride, Okay, there. If you hit strongly, it will decompose. Okay, when heated to about 150 degrees Celsius. Of course, decompose means you're going to get tin 2 chloride. Okay, so pay attention to all the physical stats. Group 14, this one very tricky. In exam, if you get all these physical stats wrong, sorry, no mark will be given. Okay, now for lead tetrachloride, definitely decompose easily. Okay, at slight warming. So, of course, you're going to get exactly the same pattern of products. Okay, you get lead 2 chloride and chlorine gas is released. Okay, now because tin and lead both are metals, so normally when we give name to metals, it's quite common we put the oxidation number in bracket. So instead of naming this one as tin dichloride, normally we definitely name this one tin 2 chloride, lead 2 chloride. Okay, but of course if it is other than that, most of the time like, when it is covalent, of course we may make use of the term mono, di, tri, tetra, and so on. But when it is ionic, normally we don't name it such a way. But still, you put such a name if they didn't say IUPAC, most of the time they cannot penalize you lah. Okay, but try not to. Okay, so that thermal decomposition. So very obvious, going down the group, the thermal stability decreases, where their tetrachloride decompose easier going down the group. Okay, now explain why we don't have this. After all, they can combine with Cl. Why not Br? Why not I? Sama-sama group 14 lah. Sama-sama can share electron, isn't it? Not to say Pb, like even CBr4 already very rare. We get CCl2, Cl4, CBr4 still can lah, not too bad. But Pb, Br4, well, does not exist. PbCl4, okay. So, why this two does not exist? Give a reason. Any idea? More or less can try to figure out what a reason you are going to use to explain this one. After all, we can get PbCl4 where Pb share electron with Cl. So how come we don't have PbBr? The so-called weak attractive force meanings which one, Joshua? You mean between Pb and Br? Why it is weak? After all, they share electrons. So how are you going to explain this one? If you get a question like this, after all, Pb can share with chlorine, so why not? Steric hindrance. Now, steric hindrance, see, normally this one is when your Pb already have other partners. Let's say your Pb already share with others, and then when this one want to come in, the others blocking the way, then that is called a steric hindrance. In this case, because Pb is just, Pb. So now you imagine the first Br want to share with Pb. So at that moment, no such thing as steric hindrance. Steric hindrance normally means it already, have other, like having other partners surrounding it. And then now there's one more one to come in. And the others, because normally due to the others very big in size, so the others will block the way. So this one cannot squeeze in anymore. So that is called steric hindrance. Get that, yeah? So here, steric hindrance is doesn't exist. Right? Never mind, steric hindrance. Next semester, you're going to deal with it. When you study all that so-called isomers, your carbon connect to, already connect to what, and then so the next one want to come in. So is it having steric hindrance blocked by the others or not? Okay. So for this one, of course, isn't it? In case you get the idea, yeah, kebat ma, isn't it? So of course, you may have something like this. Of course, it's because of the size, Joshua, I guess maybe this is what you mean, but you don't have further support of your statement just now, okay? And you cannot just say attractive force, huh? Attractive force, this term only suitable when you are talking about attraction between molecule and molecule. Then we use the term attractive force. If it is between atom and atom, most of the time you should name that bond, the types of bonding, okay? I mean, for your case, you should say because a weak covalent bond. You don't use the term attractive force. Right? Attractive force normally is for between molecule and molecule. This one because Pb and B are sharing electron. That is the covalent bond. Straight away, okay? Actually they because they're unstable, so they do not exist. Even you let them form also, they will decompose spontaneously. Okay, PbCl4 still can exist at a low temperature lah. See that? Okay, because Cl is still small, so still able, that covalent bond still able to hold. Okay. Okay, so there. Okay, thermal stability settle. Now the boiling point settle. So now, but of course, boiling point is a physical property. Thermal stability is a chemical properties. So this is also chemical property. Hydrolysis. I mean, can they react with water? Okay, hydrolysis. So let's see. All group 14 tetrachlorides, all except the CCl4, can be easily hydrolyzed by water. That means they can react with water, in other words, except CCl4. Of course, one of the product is hydrogen chloride gas, which of course seen as a white fumes being released. Okay. I mean, why they can do this? Because they all having empty d orbital. So you can imagine now, if question asks you why CCl4 cannot, there's a reason lah. Carbon, period 2, no d orbital yet. So it doesn't have empty orbital. Right? To form dative bonds with water molecule. Okay, so we check. There. So when silicon tetrachloride is added to water, of course the lone pair electrons on the oxygen of the water is donated to the empty 3d orbital of the silicon. So it can form the so-called coordinate bond. Okay, and of course the coordination facilitates the hydrolysis. That makes the hydrolysis process easy. So when these two react, you find that all the Cl4 gone, so replaced by oxygen. Okay, so the hydrolysis, that means the same take place for germanium, tin, and also lead. Do we have lead here? No, yeah, lead. Okay, silicon, germanium, tin, lead. So they all react in the similar way. Hydrolyzed by water, or should we say they all react with water. Okay. So meaning so these two separated. Okay, this one slot in, slot in. So you get the SiO2. Okay, so that is the reaction with water, except CCl4, no such reaction. Okay, that there. Carbon tetrachloride or tetrachloromethane. Okay, so cannot undergo hydrolysis because carbon atom has no empty d orbitals to receive the lone pair electrons from oxygen of the water. Okay, after all, carbon, no empty orbitals at all, okay, because the s and the p orbitals of the 2s2p have been used for sp3 hybridization and also involved in the bonding with Cl, chlorine. So no more empty. So that means totally out. That's why carbon tetrachlorides do not undergo hydrolysis. Okay, no empty d orbital. Of course, you need to know d orbital not necessarily 3D, yeah. Okay, who knows, it may be 4D. After all, it's just in d orbital lah. Okay, so that's why CCl4 inert in water, no reaction with water. That, so that settle for this part also. So now able to fill in. Okay, give you 5 minutes. Even though some I didn't talk about it. Okay, take out a piece of paper, fill in now. I'm going to ask them now, after 5 minutes. Okay, 5 minutes now. Hold on, let me get an list. Okay, so the first column, physical state. Alexander, what is the answer? Liquid for which one? Get it clear. Yep, Alex? Liquid for all, liquid for which one? State clearly. CCl4 only. The whole rows, huh? Now, all of you need to answer for the whole rows, okay? Any specific answer for which one? Let me know. So, liquid for CCl4. The others? Yes. Alex, only one? CCl4? Silicon tetrachloride, germanium tetrachloride, tin tetrachloride, lead tetrachloride. How? The others, how about GE, SN, PB? Answer for the whole row, eh? Good. Alex, answer the faster, isn't it? That means for this one, in fact, I think it's quite, well, should be direct, right? I think this one, the answer. That means the answer will be, isn't it? All of them will be liquid at room temperature. 298 Kelvin is 25 degrees Celsius, huh? Room temperature, right? So all, of course, will be same answer. Of course, I didn't say all of them will be like that, okay? Except for physical state, all of them will be liquid. Okay, conductivity of electricity. Okay, conductivity of electricity. Chan Kuyen. What's the answer? The rest can expect today for the time being now I'm going to follow the name list. What should I feel for conductivity of electricity in the liquid state? One word enough already. Most of them you only need to answer me one word, 2 words, okay? Summary Yeah, Kuyen. What do you think, sir? Conductivity of electricity.
全部不会耶。
在上课好心里用一下 Alex 会懂的字。Okay, good. Of course, after all, they're all covalent compound. Since when you study covalent compound can conduct electricity, isn't it? It's a big, all of you, isn't it? It should be, common sense question, logic, so of course answer, cannot, habis cerita, isn't it? Oh, cannot lah. After all, I said liquid, you should get the idea. Electrolyte only take place for aqueous solution because aqueous solution contain ions. These are not free-moving ions. How to conduct electricity, isn't it? Okay, next types of bonding. Grass. Covalent bond between. You need to tell very clearly. That's how all of you in the exam. For all, between. You need to tell very clear. Type bondings here. I will expect two different answers. You tell me clearly between what and what. Of course, I mean, sometimes, that of course will be exactly same answer, right? So if it is covalent, that means it is between. Okay. Other words between atom size, isn't it? Now, because I only mentioned, types of bonding, I didn't say between what. So your answer must give me two. So between atoms, okay, it is a covalent bond. Now, how about between molecules? So when you answer, you need to tell very clear. You are talking about between what? Okay, or else you are not going to score marks, Okay, now Mandy, between atom, okay, is covalent bond. Then how about between molecules? Because you should know they're all. I give answer already, isn't it? 不可以讲. So that's why if it's two different answer, you must tell very clear. Get that? Because if you only answer covalent bond, I can tell you, if I marks, I won't give you marks on. Get that? Because that is blur answer, ambiguous answer. Okay? Get that? You must tell very clear like this. Of course, you may answer one of the, one of it only. Doesn't matter, but you need to tell very clear. Yeah? I mean, if it is covalent bond, of course, it must be between atoms. Between the C and the Cl, that is, covalent bond. But between one CCl4 and another CCl4, of course, that is van der Waals. Clear? That is how you answer question, please. I mentioned so many times when you want to tell bonding or attraction, you must tell me between what. Without that, you're going to lose mark, I can tell you. Okay? Don't try, like, blah blah, and try to bluff your way. Cannot. Cannot. Okay, the next one. What is the structure of all this tetrachloride? Olivia? No, tetrahedral is a shape. What is the structure? Today in exam, 你们很大问题啊. Be very careful, The rest also, all of you. You need to try out, Don't say not my turn yet. You need to really do it so that you know. That's it. Simple molecule. That is what I'm waiting for. All of them are simple molecules. None of them are giant structure. Clear? If giant structure, also you must name clearly, giant covalent structure, giant ionic structure, or giant what? Okay? So for this one, of course, again, same answer. But I didn't say all of them will be definitely same answer. It's just coincident that until now, they're all same answer. Okay, so this one is a simple. Of course, if you want to put in, you may put in this one. But most of the time, you put simple molecule already okay. But this one very obvious, it's a simple covalent molecule. Yeah, molecule also kind of, after all, molecule definitely covalent. We got molecule ionic, okay? So then, okay, stability, no wonder it keep on red in color. Yeah, double L. Okay, thermal stability. Shelley? Same answer, different answer? Thermal stability, you only tell me stable or decompose. That's the word only. Okay? Only put in two words. Whether it is stable, it is decomposed. That's all. In fact, you put stable, unstable lah, but the word unstable, yeah, straight away tell me. If unstable means it will decompose, right? So, okay, cái này CCl4 stable or decompose? Đấy. CCl4 stable, decompose. That means when you heat, will it decompose? If it cannot decompose, stable. We just go through thermal stability, oh, Shelley. So CCl4. Is it stable under high heat? Stable or decompose?
Stable.
Okay, stable. SiCl4?
SiCl4.
你刚才上课在做什么啊？
有点飘。
啊 You see this one? You get this one?
Stable.
Well stated clearly. 这声音干嘛那么漫长？ See that, isn't it? Stable even at high temperature means even you heat them also, they're not going to decompose. See the word right? There. 这整张 slide 全部答案在里面。Get that, please. Pay attention. So for this one, that means these three stable. Save time, isn't it? Okay, so means the other two would be decomposed under high heat. Okay, that is how you should fill in that. Okay, hydrolysis. Chen Chen. That means you only tell me, can or cannot? Habis cerita. That means can they react with water? Okay, CCl4. Can or cannot? Okay, cannot. This one. How about silicon tetrachloride? Can or cannot? Okay, the others can. Good. That isn't it? So all this can be hydrolyzed. Now, of course, if can, yeah, what would be the product, Kahong? Generally speaking, what would be the products?
SCl and SCl2.
That means SiCl4, if hydrolyzed, that means when react with water, HCl and and good, oxide, okay, or you prefer, you can always put and the dioxide, okay, of the elements. That? Because they all become O2, 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 right? Or sometimes you can even put like this. Because normally we represent using MR for the elements, right? So of course, you may go for something like this. Can. Okay, the M represent, the elements of group 14. And so that is what we've been doing until now. 10点半，现在11点半 1 hour.
Nice.
Yeah? So sums up, that is what you need to know for tetrachloride of group 14. Of course, how to form all this tetrachloride, please remember. Silicon, germanium, and tin tetrachloride is not easy. The metal react with chlorine, isn't it? But for the other two, of course, it goes through different methods. You need to remember their equations. Okay, and of course, all these tetrachloride are liquid at room condition. Of course, all of them cannot conduct electricity. If they ask why, because they do not have free moving ions. Okay, they're all neutral covalent molecule. And of course, they all these tetrachlorides are having covalent bonds between the atoms, and of course, all the molecules are, attracted by very weak van der Waals forces. And then, of course, they're all having a very simple molecule. And you find that the first three tetrachloride actually very stable under even high heat. They do not decompose, but the other two decompose. In fact, PbCl4 decompose easily with slight warming. Okay, and of course, after decompose, you get the product is the PbCl2 plus the chlorine gas. And of course, they all can be hydrolyzed by water except CCl4. Okay, so that is tetrachloride settled. Okay. Now, still remember this one? How do you answer this one? Number 2. Silicon tetrachloride undergoes hydrolysis with water, but carbon tetrachloride does not. So, 1. The answer also shown already just now. This one will be, 2 marks question will be the highest you can get is score. Score will be 3 lah. I think this will be 2. 1, 2, yeah. Now, that means this one you cannot just tell about carbon now. You must tell about silicon also. You need to tell about both when you read this question. Please be very careful. That's how normally this one will be 3 marks. 2 to 3 marks. You don't just talk about carbon only. You need to talk about silicon also. Because you need to explain the statement why silicon can, carbon cannot. Okay, missing? More or less tell me. Silicon tetrachloride can because carbon tetrachloride cannot because hello. Okay. Now, if silicon, you tell clearly which D. Because silicon, its position is period 3, So that means you put 3D to form dative bonds with water molecules, okay? And then, how about carbon? Okay, so settle with silicon. Good, you get it? Okay, Essen, how do you explain about carbon? Okay, I mean silicon tetrachloride SiCl4. Missing. Okay. No, not SiCl4, the way you write. It is Si. Use the empty orbitals to form dative bonds with water molecules. Get that? Not SiCl. It's Si because Si has empty d orbital. So water have lone pair. So it will donate the lone pair and then share with Si. That okay. Now, Sn for carbon still not strong. Okay lah, no vacant d orbitals, but it has a vacant p orbitals. Why also cannot form dative bond? I need to give more clear. No vacant d orbital true, but at the very beginning, because you need to remember carbon 2s2 2p2. We all know p having 3 orbitals, So P2, that means one of the P still empty. Or how come that one also cannot form the dative bond? So that means that part you also need to write in your answer to make your answer very strong. No d orbital, okay, true. But logically carbon still have one empty p orbital. So how come? After all got empty orbitals, logically it still can form dative bond. How come cannot? Okay, we change. Jason, you answer. That means, Essen, the answer you write, good for 2 marks. Let's say if this question 3 marks, so I still need more. You need to support stronger for your carbon. Because as I mentioned, but I can query. No d orbital, doesn't matter. P orbital got all. That means you need to prove why p orbital not empty. I mean this one, if p orbital empty, actually can. But the problem is p orbital is not empty. Why it is not empty? Jason, your turn. I mean, carbon cannot because, first of all, it has no empty or no vacant d orbital. Yes. Another reason, as I mentioned, no d orbital empty. Doesn't matter. P orbital logically empty. After all, the electron arrangement is 2s2, 2p2. We all know P got 3 boxes. Not good. Not this one, Kevin. Small or big does not affect whether it can accept lone pair or not. Why p orbital filled with electrons? After all, the electron arrangement is 2s2, 2p2. Only 2 boxes filled with half spin. There's still 1 box empty. Why not? Cannot. If there's an empty box, as long as there's an empty orbital, it definitely can accept lone pair. It doesn't have d empty orbital, true, but p got all. Period 2 you got until 2p. No, except lone pair, doesn't need to be ionized. Empty orbital, you can accept already. After all, they share electrons. It's not like you want to donate electron. No, it's just share. You study already, Sharing electron, there are two patterns. One is I give one, you give one, we share together, forming a covalent bond. Another type is I have empty orbital. You have two electrons, let's come share together. That is a dative bond, or we call it a coordinate bond. Sharing also, that means as long as there's an empty orbital, one of them, and the other one have lone pair electron, then actually they can share. So in this case, carbon, and water, yeah. That means logically carbon, its valence electron is 2s2, 2p2. Four valence, 2p2. So the p orbital, we all know there are 3 boxes for p orbital 嘛，你每次画3个格子哦。So 2p2, that means only 2 box filled with half spin. There's still 1 box empty. So logically, there's empty orbital. By right, it can accept lone pair from water. But problem is, of course, cannot. The statement tells you cannot. Sorry, cannot. So why cannot? Right? 其他人 others want to try? 这几个写的答案都不对了啊。I already mentioned in my notes just now. 哎呀。That means all of you, if this one 3 marks question, your answer not strong enough. I mean, essence answer is already quite complete. Except that, as I mentioned, you said, in case of carbon, there are no vacant d orbitals. But of course, as I mentioned, I can query, but it has a vacant p orbital. So how come still cannot form the dative bond? That means you must prove that p orbital also not empty. How not empty leh? After all, 2s2, 2p2 or empty or how come it's not empty actually? In real, that means it's not empty. That's why I cannot. That's it. sp3 hybridization that means that p orbital mana the empty already filled. So you remember this part. That means in your answer you need to mention that to be very safe. Where is it just now? Here. At first, memang empty. You see that? It is empty. So if empty, of course it can form dative bond. But the problem is because carbon actually undergoes sp3 hybridization like this. You get empty. No empty already. So that means it can form covalent bond but accept 1 electron, 1 electron, 1 electron, 1 electron. Can. But want to accept 2 electron. Lone pair means 2 electrons. Want to accept 2 cannot because no empty. Good idea. But silicon can. Why? Because silicon it has 3 shells until 3. 3, that means you get 3s, 3p, 3d. You want it or not? D memang empty. D got 5 boxes. There's no way you can fill any of them. That means there are plenty empty one. So it can accept lone pair. Get it? Carbon, sorry, even though at the beginning it seems like yes, there's one empty. But carbon need to undergo hybridization first. Okay? So after hybridization, share with 4 chlorine, no more empty. Because period 2 only until 2p. We don't have 2D, you see, 2P saja. So no more. But if goes to period 3, suka-suka you lah. That means you get 3D already. If period 4 lagi hebat, you get 4F. Lagi lah. Plenty of empty orbitals. Get that? So please, that means for that question, you need to answer until this, sp3 orbitals. Okay? I think the answer here, hydrolysis just now. This one there. The answer is here, right? no empty d orbitals, also no empty p orbitals, because it have been used for sp3 hybridization, and of course already involved in bonding. No more empty one. Oxygen got 2 electrons, so need an empty orbital to share. Yeah, so that means your answer for that, the question number 2 just now, isn't it? This one lah. Okay, so that means more or less this slide lah. There. Both of the statement you need to put in. Okay? That means this one only explain carbon. Yeah? Remember, for that question, you definitely need to explain SI also. Okay? Because the question said why it is so. That means why this statement is like that. I'm not talking about why carbon is like that. If why carbon is like that, of course, you only talk about carbon only. No need to talk about silicon. Okay. But this one, why the statement is like that. So you need to explain for both. Okay, so in exam, please pay attention. You don't only explain about the carbon only. Then you are going to lose half of the marks. Okay, so that will be tetrachloride. Okay, so next, let's go into the oxide. Okay, so oxide, if you check, of course, there are 2 types. The monoxide with oxidation state +2, isn't it? And of course, the dioxide with oxidation state of +4. Okay, that means, of course, the oxidation state means oxidation state of the group 14 elements. It can be +2, can be +4. So let's look at these 2. Okay, so what do we need to study regarding these 2 types? The thermal stability and their acid-base nature. They mean their acid-base property. Okay, so for both the monoxide and the dioxide, I mean, are they stable under high heat? Or and another one is, are they acid or alkaline or maybe neutral or even amphoteric? Okay, so that will be the 2 that we're going to do. So let's start with monoxide first. Okay, so start with the first one, thermal stability. That means if I hit the monoxide strongly, is it going to decompose or is it stable unchanged? Okay, so of course, group 14 monoxides. The word is called monoxide lah, but normally, as I mentioned, when talking about metal, most of the time we don't use the term monoxide. Okay, of course, the first one, CO, carbon monoxide, of course. And then, of course, we get the Si, silicon monoxide. That, of course, next goes into germanium. Germanium, most of the time, we are going to call it germanium 2 oxide. And that is very rare. We use germanium monoxide. Germanium actually slightly still considered as it is semiconductor. Semi-metal lah. But most of the time we already use the term germanium 2 oxide. That means, of course, for the other 2 definitely is tin 2 oxide and lead 2 oxide. Okay. That means it would be very weird you call it tin monoxide, lead monoxide. Because, when we said monoxide, I always have the, impression that it is a gas. Okay, but of course, germanium 2 oxide, tin 2 oxide, lead 2 oxide, they are solid, definitely. In fact, silicon monoxide very unstable lah, to be true. Okay, it's very unstable, but still, it is solid form, at room temperature. Okay, so let's look at them one by one. So carbon monoxide, of course, is neutral. I already mentioned a little bit regarding the acid base already. It's neutral. And then of course it's a toxic gas lah, at room temperature. And then of course it is a simple covalent molecules. Just CNO, okay, it's a simple covalent molecules. Now of course we always say it's a toxic gas, of course by right you should know this one, isn't it? If you inhale CO in a very high concentration, of course the ending result, you look pinkish, and then we all need to bite you sayonara, isn't it? Of course odorless, okay, I mean no smell, tasteless, nothing lah. Okay, it burns with blue flame in air. In other words, that means it will react with oxygen to produce carbon dioxide. Okay, carbon monoxide burn in air, or should we say carbon monoxide react with oxygen, produce carbon dioxide. Or of course, we may say carbon monoxide is oxidized to carbon dioxide. Of course, the burning is blue flame. And of course, if you don't burn it, you just leave it there, well, slowly it also will be oxidized to carbon dioxide. Okay, anyway, that's carbon monoxide lah. It's a toxic gas, colorless, okay, and of course, it's a simple covalent molecules. Okay, silicon monoxide, also a simple covalent molecules, huh? And logically it is a brown black glassy solid. Then it looks like glass a little bit lah. You look at it, you already know it is not a metal. Okay, and then of course it can be changed to the dioxide by heating. Okay, that means kind of like similar as the CO just now lah. You heat it can become CO2, so this one also quite similar. Okay, so that is silicon monoxide. Okay, now of course you want silicon monoxide as a gas. Well, it must be at a very high temperature. Or in other words, you may imagine like its boiling point is over 2000 degrees Celsius. If you cool it, I mean you cool your SiO from that hot temperature of gas. When you cool it, actually it will disproportionate back to SiO2 and Si. That means this one is when it is very hot, so you let it cool, then actually it becomes SiO2 and produce. That means it becomes a mixture of silicon oxide or silicon dioxide lah, and silicon metal. Of course, I hope you still remember the terms disproportionate. Disproportionation is a reaction where the same substance undergoes oxidation and reduction at the same time. Okay, simultaneously. So so that's why we always say like SiO in solid form. Even in gas also, it is very unstable lah. But at room temperature, it is a solid, of course. Okay? So that is silicon monoxide. It is neutral also. Okay, and then germanium 2 oxide, tin 2 oxide, of course, ionic compound actually. I mean, the first two would be simple covalent molecule. This one is an ionic. Okay. Now, of course, this one simple molecule is when it is a gas. You get that? But when it is a solid, of course, it's covalent structure lah. Covalent giant structure if it is a solid form. Okay, so these two, of course, solid lah. Ionic solid, but of course with a covalent character lah. Okay. And of course, they can be oxidized to the dioxide easily. I mean, same thing lah. React with oxygen becomes the dioxide. React with oxygen becomes the dioxide. Okay. And then, okay, this one, of course, also ionic compound, yellow. Of course, this two will be white solid lah. Of course, this one is a yellow solid. PBO, you should know. PBO, when it is cold, it is yellow. Now, what's the color when it is hot? Joshua? PBO, when hot, what's the color? No, Chung Yu, no. No. Joshua? Okay, so you correct. Brown color. And this one you study in Form 4 lah. Okay, I mean, for example, the most popular, zinc oxide. What's the color when hot and when cold? Still searching. I already mentioned the color. Oh, I got pisang goreng. Okay, good. There, zinc oxide, you remember. It is, yellow when hot, white when cold. So, of course, another one which you need to memorize in your Form 4 is PBO. Lead 2 oxide, it is yellow when cold, brown when hot. Okay, that means that will be the 2 oxide which change color when temperature change. So PBO, of course, is a yellow solid lah. Okay, of course, ionic compound, but with a quite strong covalent character. Okay, and then of course, it is stable to heat. In other words, it's not going to decompose easily lah. Okay, so if you heat it strongly lah, but still stable to heat also, if you heat strongly, let's say above 400 degrees Celsius, then you find that, of course, it still will be converted to, but you need to know it's not converted to, like PbO4, whatever. It is converted to a triplumbum tetraoxide. Of course, the term plumbum, more direct lah, because Pb actually Latin is plumbum, or we call it the dilead 2 lead 4 oxide. Don't ask me why like this, because it is the name. Okay, because the term is, dilead, that means Pb2, and then lead 4 oxide is a PbO4. So actually, it kind of like split. This one is Pb2 and then PbO4. So that is the common name, you see, dilead 2 and then lead 4 oxide. Oh, of course, should we say the more direct is triplumbum, 3Pb lah, isn't it? And then tetraoxide. Of course, the one in bracket is the IUPAC. When you see the bracket thing like this, that means that is an IUPAC pattern. Without that, you see a di, a tri, whatever in front, that is a common name. Okay, that's PbO. So it's an ionic yellow solid. Okay, so that PbO, if you let it heat above 400 degrees Celsius in excess oxygen, you find that, of course, it will change into Pb3 or 4. Okay, now this one, of course, is a mixture of PbO and PbO2. I don't know why some folks they put it like this, but when you look at the name, it seems very weird, isn't it? It's kind of a dilead 2. You get a Pb2 and then a PbO4. But in real, it is this one actually. It's a mixture of, lead 4 oxide and lead 2 oxide. It's a mixture of them. Okay, now, however, of course, just now we said you heat until 400 degrees Celsius, your PbO will, become this one. However, on continued heating to about 440 degrees Celsius, you find that this product actually will convert back to PbO again. Okay. Now, of course, this one will be more interesting. So, I did not say anything lah. That means if you briefly go through Carbon monoxide, okay, is a simple molecule, colorless gas. SiO, okay, at above 2000 degrees Celsius is a simple molecule gas. But SiO at room temperature actually would be a black glassy solid, which of course in a covalent giant structure. And then you get GeO, SNO, they are ionic solid. Okay, and of course if you heat them, they would become their dioxide. That means same as CO lah. CO you heat, it will become CO2 lah. And then this one, PbO, okay? PbO, of course, quite stable under heat, but if you heat over 400 degrees Celsius, it will become Pb3 or 4. Keep on heating, actually it will convert back to PbO again at 470 degrees Celsius. Okay? Now, of course, this one, this triplatinum tetraoxide. Okay, if you heat with dilute acid, nitric acid, yeah, you find that it will form, it will dissolve, that means it will react lah. Dissolve normally means it can react, okay, it will forming a colorless solution and a brown solid of lead 4 oxide. And then when these two react, you are going to get your, this one brown color, brown solid, and then this one, your lead 2 nitrate, a colorless solution, and plus water. Okay, so in fact, when these two react, you get a brown precipitate lah, actually. That? I mean, this one is a brown solid lah, in this colorless liquid, so you are getting actually the brown precipitate. Okay, and of course, colorless solution, normally we don't really mention. Why? You imagine these two, when you react these two, isn't it? This one is red in color. Is it just now? There, red. Red solid. So that means the red solid, when you let it react with an acid, isn't it? Dilute acid, you heat them, then you get a brown solid. Okay. And of course, lead 4 oxide, PbO2, if you let it react with sulfur dioxide gas, then you find that actually you are going to get the white lead sulfate, lead 2 sulfate. This way of writing actually not so good, isn't it? No? Because this one is continue from the one on top. And that continue because here your PbO2 is it's a precipitate in a solution. So that's why it says, when you bubble the gas through that solution, then you find that the brown precipitate would becomes white precipitate. That means it becomes a white color. But of course, if you let these two react in terms of equation, because PbO2 definitely is a brown solid. If you let it react with SO2, then you're going to get brown becomes white in color. Okay? So in other words, you find that if we have a look at it, because most of the monoxide, when heat will become dioxide. Monoxide oxidation number is positive 2. Dioxide oxidation number is positive 4. So you find that most of them, if you heat the change, that means of course whatever the change to, that one should be more stable, isn't it? So that means the positive 4 oxidation state, are more stable than the positive 2. But for lead, of course, you find that no. In fact, you see most of them, it will change back to Pb2. So for lead, positive 2 oxidation state is more stable. Okay, so that is briefly regarding the monoxide. Okay, that means the monoxide of carbon. Carbon monoxide is a simple molecule, it's a gas. And it can change to the dioxide easily by heating only. You leave it there also, it can, oxidize to the dioxide slowly. SiO, of course, is a gas at temperature, 2000 above. That. And then if you let it cool down, it actually disproportionate to SiO2 and Si. And then germanium oxide, you heat, it will become germanium dioxide. Tin 2 oxide, you heat, it becomes tin 4 oxide, the dioxide, isn't it? Except PB. Can, hold on, briefly summarize this part first. Right? So for PB, very obvious. Most of the product will be stable at PB 2, okay, not the 4. I mean, you prefer change back to 2. Okay, so of course the next part, the acid base. I mean, you just need to know whether it is acidic, it is base, or it is amphoteric. So if acidic means it's supposed to be able to react with alkali, isn't it? If it is base, it should be able to react with acid. If it is amphoteric, it can react with both. Huh? Okay, so we settle for this part first, okay? And then I'll let you take 10. This one just brief only, just need to know. Okay, so the monoxide, these two, neutral. Neutral means they cannot react with acid, cannot react with alkaline, logically. But of course, CO, if you bubble it through concentrated alkali at high temperature, you find that it still actually will react. Because by right neutral, neutral no reaction with alkaline or acid. But if your alkaline is concentrated, temperature is high, then actually CO having an acidic character now, so produce salt. And then acid plus alkaline, you get salt. But this one only under extreme condition lah. See that now? Or else these two, of course, neutral. That's the thing you need to know. So the next one, these three amphoteric. So amphoteric means they can react with both acid and alkaline, produce salt and water, isn't it? Or at least produce salt. So, okay, that means all these three can react with hot and dilute acid, forming salts and water. Okay, so react with acid, you get salt and water. Now, of course, for this one, please, the ion that represent acid is hydrogen ion. No, don't get them confused. So imagine if your acid is HCl, then of course your product here is GeCl2. Okay, that the salt, germanium chloride. Okay, so salt and water. So similar, tin. Tin react with acid, you get salt and water. So PB also the same. Lead react with acid, you get salt and water. So you imagine if your acid is sulfuric acid, H2SO4, then your salt is PbSO4. Okay, so it depends on the acid you're using. Now, of course, they also can react with alkaline, isn't it? But you just need to know, react with alkaline, the product is only salt. That because the water is written before, not salt and water, this one you sendiri hafal lah. That means the water is before the arrow. So, for example, germanium monoxide or germanium 2 oxide react with sodium hydroxide and water. So your product is a salt. That is a sodium salt. Of course, you need to know all sodium salts are soluble. So aqueous solution now. Okay, so similar for tin. Of course, react with alkaline. Let's say I do not want to mention what alkaline I'm using. So alkaline is represented by OH, hydroxide ion. So the salt, that means you only don't see the Na in front. Who knows, I'm using KOH. If KOH means my salt is K2, potassium salt, isn't it? So similar with tin. Okay, because these three monoxide are amphoteric. They have both the acidic and the basic property. So they can react with both acid and alkaline to produce salt, or at least salt and water. So there, briefly summary. So in terms of thermal stability, of course, we may assume PbO is quite stable. Okay, of course, stable or not depends on temperature lah. It is stable below 400 lah. Above 400, it will decompose. Not to say decompose lah, but it will change to, the PB3O4 just now, isn't it? But when you keep on continue heating, actually it will goes back to the PBO again. So it is stable lah. But the other three, of course, they are unstable. They can easily becomes their CO2, SiO2, even though the process like SiO, the process that it changed to SiO2 is slightly different lah, isn't it? CO plus oxygen becomes CO2. GeO plus oxygen becomes GeO2. SNO plus oxygen becomes SNO2. But SiO, of course, not plus oxygen. This one disproportionate, isn't it? SiO becomes SiO2 plus Si. Of course, equation half scenario. Okay, physical state, of course, the rest are all solid except, CO is a gas, isn't it? And then structure, of course, well, SiO in gas form definitely is a simple molecule lah, but you need to know lah, SiO at gas over 2000 degrees Celsius is not really stable because it will disproportionate back to the SiO2. See that, this three, of course, ionic structure lah. Ionic means giant structure lah. CO is a gas lah, simple molecule lah. And of course, in terms of acid-base property, of course, the first two neutral, the other three amphoteric. Okay, so that is monoxide. Okay, so we take. Let's see how long. Take. Hold on. Now it's 12. Okay, so give you about 12:15. I will come back and then we settle for dioxide. Then we finish. Dioxide also we study only two. I mean the thermal stability and the acid-base property. That's all. Where got 12:50? 12:15. 1-5. And then we continue. Dioxide habiskan. Only two parts very fast lah. Because some of you are asking for rest for a while, okay? So I take 5 little bit. I let you have until 12:15 then come back. Oh. Welcome back. 全部人回来了啊 Nobody missing 啊 Okay, so let's settle. Continue with dioxide. So of course, quite similar. We are looking at the thermal stability. I mean, if I hit this one, will it decompose? Or will it become something else? And of course, also looking at is it acidic, basic, or what? Okay. So let's see. Okay, dioxide of the group 14 and their thermal stability. Okay, so first of all, the carbon dioxide and the silicon dioxide, or you prefer silicon 4 oxide, okay, will be covalent. Okay, whereas the oxide of the others would be, ionic lah. They are covalent with ionic character, but normally, well, we may assume they are ionic lah actually, okay, ionic compound. But still covalent can lah. Okay, So, I mean, dioxide, carbon dioxide, very obvious, simple molecule, isn't it? Gas, but silicon dioxide or silicon 4 oxide, of course, is a giant covalent structure. Okay, so let's have a look now. Dioxide of the first three, the first four, in fact, carbon dioxide, silicon dioxide, germanium dioxide, tin dioxide, or most of the time we said tin 4 oxide, germanium 4 oxide, silicon 4 oxide, okay? Carbon dioxide, of course, they all can be prepared by direct combination of the elements with oxygen. Okay? That means carbon plus oxygen, you can get carbon dioxide. Of course, CO plus oxygen, you also get carbon dioxide. Okay? But of course, you let the metal directly hit in oxygen, you are going to get the dioxide, in fact. Okay, but PB, of course, slightly different, isn't it? Now, PbO2, this one, lead 4 oxide. PbO2, okay, is usually prepared by the electrolytic oxidation of lead 2 in acidic solution. So that means this one, normally we do not obtain by direct heating. Because if you Pb plus oxygen, you're going to get PbO. And then you're not going to get PbO2. So PbO2, that means the way of prepared slightly different. Okay, so all the dioxide of carbon, silicon, germanium, tin, stable to heat. But of course, Pb definitely no. So if we check now, carbon dioxide, of course, thermally stable. And of course, it's a gas, okay, at room condition. Okay, in fact, it's a simple covalent molecule, non-polar, okay? So in the carbon dioxide, of course, the carbon undergoes sp hybridization. Always remember when sp means you're going to get double bond, yeah? Normally sp is what linear shape, CO2, isn't it? Okay, next, silicon 4 oxide, SiO2. So of course, it is a thermally stable solid. Like that. Very high melting point. This one, in fact, we go through when you study period 3 that day. And then it's a giant covalent lattice. That means giant covalent structure lah. Okay, or you prefer, you can always use the term giant covalent lattice structure. Okay, that means with a structure quite similar to diamond, where silicon, okay, is a sp3 hybridized. Remember this one? One Si connect to 4 oxygen, and each oxygen connect to 2 Si. Okay, I mean the shape quite similar to diamond lah, except diamond, all of them are carbon atoms, isn't it? This one consists of, 2 types of atom. No? Okay, and then germanium 4 oxide, tin 4 oxide. Of course, also thermally stable solid. Right? And then of course, both gave structures intermediate between giant covalent and giant ionic lah. But most of the time, we classify them as ionic compound. That means in exam, if you write their structure as ionic giant structure is okay, accepted. Okay, PbO2. Now it's a brown solid. PbO also hot, also brown. This one is a brown solid. Okay, with structure also intermediate between giant covalent and giant ionic lah. Normally we classify as ionic compound. Okay. Well, this one of course thermally unstable. It will decompose. Okay, back to PbO when you heat it to about 300 degrees Celsius. Okay, PbO2 back to PbO. Okay, so that is thermal stability. That isn't it? That be the case. Of course, in terms of structure, if you want to include, isn't it? If we include in terms of structure. Okay. So what should I feel for CO? Kevin? What's the structure for CO2? Oh, sorry, CO2. I mean, carbon dioxide. Kevin, answer. Kevin, 人有在吗？ No structure, not shape. 就是一个了哦。Structure, you don't get them confused. When you want to explain their melting boiling point, you must mention their structure. Yes? Yeah, Sun Kai get it correct. This one is the answer is a simple molecule. And that's how you answer structure. Don't get them confused. Emma, don't let you try. You all get it correct. Go all get all the wrong terms. Okay. How about SiO2? 张思雨. What's the structure? Silicon oxide. That's it. This one is a giant covalent. That. Now, how about GO2? 张宇.
Giant covalent.
Not really giant covalent. This one, of course, might not just sound I'm giving. Isn't it? I think I give you this term. In fact, I think these three will be quite similar answer. Then intermediate between giant covalent and ionic. In fact, it will more towards ionic in fact, there will be more towards ionic compound. Now it's ionic covalent, giant covalent, ionic giant covalent, giant ionic. Physical state. Of course, I mean physical state means at room condition now, of course. Physical state at room condition. CO2, 松开。
老师我嘞？
谁漏掉了？
刚刚我不小心退出去了。
我知道，我看到你退出又跑进来。Giant covalent, okay lah. Your answer just now, okay? Physical state, this one, of course, gas. SiO2, Sophia. Okay, good, solid. In fact, I guess all the rest here would be solid, isn't it? Okay, at room condition. Okay, that now. So briefly, that's the thing you need to know lah. Okay, about the dioxide. Okay, I mean for this one, of course, the bonding CO2, in fact, all of them lah would be more towards covalent between molecules. Sorry, I mean covalent between atoms. And for CO2, of course, is van der Waals forces between molecules. Okay, but the rest, that means all covalent only, because they're all connected now, especially SiO2, very high melting point. Okay, so briefly, so that means all of them very stable at high temperature. That means they are not going to decompose. They prefer to maintain as the dioxide, except lead only. Okay, and prefer to presence as a monoxide. Okay? So the external stability. Okay, the last part. Are they acid? Are they base? Are they amphoteric? Okay, of course, CO2, SiO2, both acidic. In fact, CO2, is slightly soluble in water, forming the carbonic acid actually. So this one very obvious acidic lah. But of course, SiO2 you cannot prove that it form an acidic solution lah because it is insoluble in water. I mean the CO2 dissolve in water, isn't it? You bubble it into water, then you get the so-called very weak acid lah, carbonic acid. So these two acidic. Okay, so acidic means of course it can react with alkaline. So it will react with sodium hydroxide, producing, well, salt and water. Okay, except the salt here is, the carbonate salt. But of course, sodium carbonate soluble, because all sort of sodium soluble in water. So for this reaction, you bubble a colorless gas into a colorless solution. Your product still a colorless solution. So basically, no visible change. You don't see anything. Okay. Okay, silicon dioxide also acidic. So of course it will react with sodium hydroxide. I mean dissolve in hot and concentrated sodium hydroxide, forming the silicate and water. Salt and water. Okay. Because sodium salt again, of course soluble. Okay. Now, of course, silicon dioxide, of course, a little bit special lah. But we classify this one as acidic, But actually, you find that it actually also soluble in concentrated acid, hydrofluoric acid, forming a complex ion. Okay, that I mean this one actually dissolve in acid, but this one is a very weak hydrofluoric acid lah. So becomes a complex ion. So in fact, this character for SiO2 make it, because SiO2 is a major composition of glass. So that's why hydrofluoric is not stored in glass containers, because it will react. And that. And then you find that if you store your HF in a glass container, you never know, one day your glass container totally dissolve already. Okay, but of course the reaction is slow. Okay, it's very slow lah. But still, that's why in lab, this acid you do not store them in glass. Okay. Under normal situation, alkaline you do not store them in glass, because this one acidic. It will react with alkaline, So alkaline solution, if you store in a glass container, that means you let the two react. Then actually this reaction take place. Get that? That means your container will slowly melt. Okay? So alkaline never store in a glass container. Because you like it or not, all glass definitely contain SiO2. because glass is made of SiO2, sand. Okay. But that means the exceptional case is this acid lah, HF, okay, hydrofluoric acid. Okay, now dioxide of germanium, tin, and lead, amphoteric. That means compared to monoxide just now, carbon monoxide, silicon monoxide, both are neutral. The other monoxide amphoteric. That so now when you compare to dioxide, the first two dioxide acidic, the other three, well, still amphoteric. So meaning they can react with both the acid and also the alkaline. So when they react with acid, okay, these two, okay, germanium dioxide, tin dioxide, okay, they react with hot and concentrated, let's say hydrochloric acid, produce salt and water. Okay? So the salt actually is the tetrachloride, yeah? See that? And of course, make sure you pay attention regarding all the physical state. That, or else you tend to make a mistake on this part. Be very careful about the physical state. Okay, and then the lead dioxide, yeah? Or you said the lead 4 oxide. Okay, this one also react with hot and concentrated hydrochloric acid, but the product is different. See that? They mean all the three of them can react with acid, but they will give you different product. So this one, the product is a, lead 2 chloride and chlorine gas, and of course, and water. Sometimes if you're scared, you're getting confused. Now that is hot. If your acid is cold, then you find that you're going to get the PbO2. The PbCl2. CL4, sorry.